Today, Karen, we're going to be talking about some terminology, the difference between resistors that are in series and resistors that are in parallel. So a series circuit is a circuit where resistors are connected in a row with no junctions between them. Example 1 says, given these two circuits, which one shows resistors in simple series? That one does. Because if you follow the current, it moves through, there are no junctions between them. Here we have a junction and a junction. Those are not in series. So, two resistors are in series if there are no junctions between them. Example 2 says, analyze the following circuit. So it looks like we have a 48 volt source. Looks like we have 4 amps flowing from the battery. Well, how many amps are going through this 3 ohm resistor then? Darman, how many amps right here? How many amps right here? How many amps in here? How many volts do I lose going through that battery then? Now, probably we should have done this. V equals I times R and power equals V times I. Or we should have those on our sheet in front of us. How many volts? Do I know the current? Say yes. Do I know the resistance? You might even be able to do it in your head. Okay, we lose 12 volts. How many amps right here, Darman? How many amps right here? How many amps going through the 4 ohm resistor? How many volts do I lose going through the 4 ohm resistor? Good. How many volts did I start with? How many do I lose in this top one? How many do I lose here? How many volts are left? No, you're right. Is it 20? I think it's 20. Okay. So there's 2 ways I can get that 20. You used Kirchhoff's law for voltage. You said whatever voltage you gain, you have to lose. You can say that's 20. Or how many amps are down here, by the way? You could have gone 4 amps, and you could have gone I times R is 20 volts. But we got the same answer by skiing using Kirchhoff's laws. The fact that we got the same answer both ways, it's unlikely we made a mistake somewhere along the way. I think all of our numbers are right. Okay? So it says fill in the voltage drops in each resistor. We did that, 12, 16, and 20, for a total of 48 gained and 48 lost. Can you find a mathematically equivalent resistance if there was only 1 resistor instead of 3? Okay. George, get the R by itself in Ohm's law. What was the total voltage in this circuit? 48. What was the total current in this circuit? What's the mathematical, if we replace this circuit with 1 resistor, what would its mathematical equivalent be? I'm going to argue then that this circuit with a 48 volt battery and a 12 ohm resistor is mathematically identical to this one. Mud, how many ohms was this top resistor? Is there a 12 hidden in there anywhere? Okay. How can I combine resistors that are in series? You just said it. Add them. That's the easy one. If you want me to replace a bunch of resistors with their single mathematical equivalent, if they're in series, R total is R1 plus R2 plus R3 plus R4 plus R, however many are in series. Okay. I only rewrite a circuit as its mathematical equivalent as a last resort, but I will give you some, Danica, that are challenging enough that after we've exhausted all of our strategies, we'll say, well, I guess I got to rewrite this as its mathematically simplest equivalent, and then I can use V total equals I total, R total. Okay? Example 3 says, select the best answer for the voltage drop across the 20 ohm resistor. 100 volts, more than 50 volts, less than 50 volts. And convince me. I think we can be more specific. Paige, how big is this resistor in ohms? How big is this resistor in ohms? Are they in series? Are there any junctions between them? There are no junctions. They are in series. I can rewrite this as a single resistor. How big? Yep. In other words, Paige, I'm going to argue that this circuit is the same as a 100 volt battery and a single 25 ohm resistor. You okay with that? How many volts from the battery, Paige? How many volts must I lose going through this mathematically equivalent resistor then? How many amps going through here then? Okay, so I can say to myself, I know I must be losing all 100 volts through there. V equals I times R. How would I get the I by itself? How many amps right here? So you ready, Paige? Look up. How many amps right here? How many amps right here? How many amps leaving the battery? This question's going to fall apart. Because how many amps right here? 4. How many amps up here? How many volts must I lose exactly going through this resistor? I times R. I times R. How many volts going through here? Sorry, how many amps going through here? How many volts must I lose going through this resistor? I can either go I times R, 80, or I could have said, I'm starting with 100. How many did you say I'm losing here? Leaving. I can get there two ways, but I can tell you for a fact that's exactly 80 volts. So it says select the best answer for the voltage drop across there. Paige, is it A, B, or C? What's the best answer? For the... Yep. Explain your answer. There's my proof. This would be an example where I might choose to combine them as their simplest mathematical equivalent. My goal for solving a circuit, it's almost always to try and find and the total current leaving the battery. If I can get that, the question's going to fall apart. I also did a couple of other things. There was nowhere where I knew two things, so I couldn't use that strategy. I checked. So, example 4 says, find the total resistance and current, and then find the current through and the voltage drop across each resistor. In other words, solve this circuit. First thing I would do is I would label downhill. The current is going this way. Electrons are actually flowing in the opposite direction, but you're starting to see why, Garrett, it's nicer to pretend the positives are moving downhill because it just makes it a much easier way to think. Zach, do you see amps anywhere on this circuit? Because I would look for that first. Do I know the total current leaving the battery? Sure, no. Okay. Next thing I would do is I would say, are there any resistors where I know two things? Do I know two pieces of information on this one? Okay, so that doesn't work. We're going to make a list eventually of my checklist, the order we solve these in, but I'm just kind of building it organically right now. What if I ski? How many volts am I starting with? How many volts am I losing here? Don't know, don't know, don't know. If I knew two of those, I could figure it. Like if this was 30 and 40, this would be 30. Okay. As a last resort, which we're now at, I'm going to rewrite this as its mathematical equivalent. These three resistors, Zach, are they in series? Then what can I write that as a single resistor? 25. Okay, so I'm going to do a quick sketch, and these, I'm not doing a fancy schmancy diagram. I mean do a quick sketch underneath here. Just say, okay, there's my battery. And that's the same as a 25. I don't even do the proper symbol. I just stick it in there. How many amps are going through this? So you ready? Sorry? Say it loud. Yeah, because how many volts must, if that's the only resistor, it's got to be losing all 100 volts. So Zach, how many amps right here? 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 Leaving the battery? This question's going to fall apart. Now I can go to my actual diagram. Oh, how many amps in that top one? How many amps in the right-hand one? How many amps in the bottom one? And now I know two things. I can find voltage or power. They didn't ask for power, so I'm not going to bother, but they did ask for voltage. I'm going to go I times R. I guess that top one is 60 volts. We lose 60 volts going through there. I times R. I guess we lose 20 volts going through there. I times R, 20 volts. Or I could have gone 100 minus 60 minus 20 leaves me 20. If resistors are in series, you can just rewrite them as a single resistor by adding them up. What if they're in parallel? Trickier. And this is where you're going to want your calculator handy. We may even introduce you to a new button on your calculator. Yes. One you've taken for granted. So a parallel circuit is where resistors start and end at the same voltage, the same height. So they're directly connected at the top and the bottom with no other resistors in between. Example 5 says, which circuit shows resistors in simple parallel? This top one here. And I'll prove it to you. You know they're in parallel if they also have identical voltage drops. Let's suppose this battery was 50 volts. Here's a possible ski run. How many volts must I lose going through this resistor then? How many volts must I lose going through this resistor if I follow this path? How many volts must I lose going through this resistor if I follow this path? They're in parallel because they all have identical voltage drops. In my ski hill analogy, Taryn, all of us got off the chairlift together and then we split up. Some of you went down this hill, some of you went down this hill, some of you went down this hill, but we all met up right there at the bottom. Parallel. This one here has one parallel branch, but these two are in series. Now, I could combine these two. I could add them together as a single resistor, and then I could rewrite that as this. I could turn it into a simple parallel where those two are in parallel, but that's not what they gave me. These two, if this is 20 volts, this is not 20 volts and 20 volts. These two will add to 20, but I don't know more than that. How do we calculate total resistance when they're in parallel? There is a proof, but I'm not going to walk through it. I'm going to tell you we can't find R total. What we can find is its reciprocal. You can find 1 over R total, and that's equal to 1 over the first resistor in parallel, plus 1 over the second resistor in parallel, plus 1 over the third resistor in parallel. Dot, dot, dot. Example 6 says, find the total resistance, R total, the total current, I total, and the current running through each resistor. Now, I got to be honest, this particular circuit, I can actually solve. Get your phone, you're okay. I know you're going to be distracted the whole time. I know teenagers. Put it carefully on top of the sink, and that way you know it won't accidentally fall. There you go. I don't need to rewrite this because, well, label downhill, Mr. Dewick. Why don't I need to rewrite this? Nick, how many volts are leaving the battery? Whee! How many volts is going through there? I know 2 things. I can find the rest. How many volts is going through there? I know 2 things. I can find the rest. How many volts is going through there? I'm going to do it that way, and then I'll do it the rewriting it method to just see if we get the same answer as a check. So I'm going to say, you know what? I know this is 36 volts, I guess 3.6 amps. I did the math in my head. This is 36 volts, I guess 9 amps. This is 36 volts, 1.8 amps. So I didn't actually need to use this, but now let's do it this way as a check. What if I wanted to rewrite this? Oh, by the way, what is the total current then flowing through this particular circuit? Well, I got 3.6 amps and 9 amps and 1.8 amps. When they all join up together, how many amps? 14.4, is that right? Okay. Or I could go like this. I could combine this 10, this 4, and this 20. The 10, the 4, and the 20 are in parallel with each other. So write this down, but don't go to your calculator yet. I could go 1 over R parallel, there's my abbrev for R parallel, equals 1 over 10 plus 1 over 4 plus 1 over 20. Write that down and then just pick up your calculator, but don't type. One way to type this, and I'm not going to take marks off if you do, would be to do this the long way. Don't type it this way. But you could go 1 divided by 10 plus 1 divided by 4 plus 1 divided by 20. Hit answer, and then go 1 divided by that. But your calculators all have a reciprocal button. It's a little x to the negative 1 button. Mine is right there. Find your little x to the negative 1 button, and the shortest way to type this is you could just go 10, 10, take the reciprocal please, plus 4, take the reciprocal please, plus 20, take the reciprocal please, and hit equals. You get 0.4. If you can't find your reciprocal button, now is the time to ask. Pause the video. And this brings us to by far the most common dumb mistake. This is not the answer. We have not found R parallel. What have we found? 1 over R parallel. So now that you have this, hit your reciprocal button one more time. That'll take the reciprocal of the answer. That's the equivalent resistor, 2.5 ohms. Now, can I be fussy and pedantic? Look up. I won't take marks off. If you do this, don't write this down. If you say that equals 2.5, except it doesn't, you've taken the reciprocal of that answer. So I always just draw an arrow, and now I'll say R parallel is 2.5 ohms. Technically, that does equal that, but that doesn't equal 2.5. It equals 0.4. You took the reciprocal. So here's what I'm arguing then. The mathematically equivalent circuit looks like this. 36 volts, 2.5 ohms. If you go 36 divided by 2.5, do you also get 14.4? I hope you do. Okay? So there is not an algebraic proof, but at least a numerical proof that that's how you can combine resistors in parallel. We got the same answer as we got by just using Kirchhoff's laws. I think I put that on your formula sheet, or did I? Did I put the rules for combining resistors on your formula sheet? I used to not, but I think I mellowed. I'm getting old. So, example 7, it says find R total and I total, then find V, I, and P for all resistors. Now, I gotta be honest, I could solve this without rewriting this, except they told me they want me to. So, I can't find R total. What I can find is 1 over R total. That's going to be 1 over R parallel, which is going to be 1 over 10 plus 1 over 15 plus 1 over 20, and then I'll take the reciprocal of that. Try that on your calculator, please. And I get a yucky answer, but that's okay. I get 4.61538, 4.61538, 4.61538, 4.61538, 4.61538. Okay. In case you're wondering, as a fraction, it's 60 over 13. I'm going to use my answer button, but I can tell you our total is what did I get, Mr. Dewick? 4.62. I would, because I'm going to use this, I would carry extra sig figs, but I'll report it as 4.62 ohms. What's the second thing they wanted me to find after I total, Braden? Sorry, after R total. I gave the answer away. So I total is going to be V total over R total. I took Ohm's law and I got the I by itself. Braden, what's the total voltage in this circuit? It's the chairlift battery. What's R total? I'm going to write 4.62, but you know I'm using my answer button. So it's going to be 60 divided by answer button. And lo and behold, I get exactly 13 amps. I would probably put boxes around these to help the marker, also because I know I'm going to be using these. Oh, geez, do it. And right away, as soon as I know the total current leaving the battery, I would label it. Now it wants me to find V and I and P for all resistors. Okay. I think now I would use Kirchhoff's laws. So I would label downhill. Taryn, do I know the total current leaving the battery? This question's going to fall apart. Do I see amps anywhere else? That's the next thing I would check. Be obvious, no. Okay. Next thing I would say is, do I have any of these with two things? Okay. Third thing I would try is, can I use my skiing voltage trick? How many volts do I gain from the chairlift battery? Did that get me down to the bottom? How many volts must I lose going through there? Knock, knock. Knock, knock. I know two things. Now I can find everything else. How many amps? Well, current is voltage times resistance. In your head, 60 divided by 10. How many watts? Power is V times I. So 60 times 6, 360, I think. Yes? I can repeat the same trick, but I can repeat the same trick for this loop. How many volts must I be losing through this resistor? How many amps? How many watts? 240. How many volts must I be losing through this resistor? 60. Or I could do it this way. Taryn, how many amps are leaving the battery? How many amps are leaving the... How many went down this path? Leaving? Leaving 7? How many went down this path? Leaving? I know there better be 3 amps there. Go I times R is 3 times 20, also 60 volts. So I've confirmed it two ways. I've confirmed it using Ohm's law and by skiing. I've got to be right. So that kind of makes sure we didn't make any other silly mistakes anywhere else either. And power is going to be V times I, 60 times 3, 180 watts. There, I've solved whatever they wanted me to find in this circuit. Okay. By the way, what if this was a circuit and I didn't know any of the numbers and I wanted to find the voltage drop, let's say in that resistor? What I could actually do is I could touch a voltmeter right there and right there, and that would give me the voltage drop. This is why voltmeters always have 2 prongs, and you measure voltage drops in parallel. We'll talk about that more later. Ooh. I like example 8, I like example 8. Example 8 is a nice question. This is approaching the level of difficulty I'm going to expect you to handle. And by approaching, I mean C minus or C. level of difficulty.
What's a B or...
We'll get there. Okay. It says find the voltage and the power lost in each resistor and find... Ooh, they didn't tell me the total battery this time. Okay. First thing I'm going to do, label downhill. The circuit current goes that way, that way, that way, that way, that way. Oh, and do I know the total current leaving the battery? This question's going to fall apart. Do I know how many amps went this way and went this way? Say no. Do I know how many amps went this way and this way? Say no. Do I know how many amps went this way and this way? Well, I think if those two are identical resistors, I'm betting it's 2.5 amps and 2.5 amps, but I'm not totally sure, so I'll walk away from that. Do I have any resistor with two things? Can I knock, knock? Who's there? I know two things. No. What if I try skiing? Oh, do I know the height of the chairlift? Not going to help me. As a last resort, we're going to rewrite this. Now, we need to notice these two are in parallel with each other. I'll combine them. These two are in parallel with each other. I'll combine them. These two are in parallel with each other. I'll combine them. But I won't go combining all six. They're not all in parallel with each other. So here, I'm going to go 1 over R parallel equals 1 over 10 plus 1 over 15. And then I'll take the reciprocal of that. What do you get? I think this will work out to a nice decimaler number. I don't think it'll be a yucky repeating. Pardon me? No, you forgot to take the reciprocal of your answer. Rookie. What? You're right. Say it again. Okay, patterns. Ready? Built-in error checks. First of all, Braden, they're not going to be that small. However, there is a built-in error check. What's this resistor, Gabor? This one? I know the parallel will be smaller than the smallest resistor in there. I know it's going to be less than 10. I know when I combine these, it's going to be less than 12. When I combine these, it's going to be less than 5. You can survive without that, but that's just handy looking for typos. So what did you tell me this one was? Okay, so we're going to do all of us a sketch here. Here's our mystery battery, and we're just going to put a 6 ohm resistor right there. I'm not even going to do a fancy circuit diagram with the wavy lines. I'm just doing a rough sketch. Okay, I should write this down. 6 ohms. Here, I'm going to go 1 over R parallel is 1 over 20 plus 1 over 5. What can I replace this with? 1 over 20 is 0.05. 4? I'm getting 0.25 in my head, and I think the reciprocal is it 4? Yeah. Ooh, I'm impressed with myself. And so in my little sketch down here, I'm going to put a little 4 ohm. And I've got some room to combine these two. 1 over R parallel is 1 over 12 plus 1 over 12. That should be 6. Double check me, but I'm pretty sure you get 2 over 12, which when I flip is 12 over 2. Is it 6? Yep. So Mud, this is my really quick sketch. How does this help me? These three are all in series with each other. Okay? Which means now I can tell you our total. It's just going to be 6 plus 4 plus 6. Oh, and in your head. Okay, one more quick sketch then. You're telling me that this circuit here is the same mathematically as a 16 ohm resistor. But also, remember I said this question's going to fall apart? What else do I know? I know the total current flowing through how many amps are leaving the battery? which means in my mathematically equivalent one, how many amps must be going through there? I wrote ohms. How many amps must be going through there? 5. Oh, and how many volts do I lose going through there? How could I calculate it? More specific than with these numbers here. How could I calculate it? Which is what? 80, you're saying? If you're not going to, you could go to your calculator. I think it's 80, yes? So, oh! How many volts must be coming off the battery if I was able to lose 80 volts in this resistor?
80.
Okay, let's put the 80 here, and let's go sprinting back to our main diagram. 80 volts. Does that help at all? Well, how many volts right here, Xavier? How many do I lose going through here? Don't know. What? 80? Then that would leave me none and none. This circuit would not work. How many volts do I lose going through here? Don't know. Wait a minute. This middle sketch. 80 volts, yes? Oh, and how many amps are going through this top mathematically equivalent resistor? How many volts must we be losing in this top branch then? How did you get the 30? You're right. How did you get the 30? V equals what times what? I times R. Okay? So, Xavier, I disagree with you. You know how many volts I lose going through there? 30 volts. 30 volts. Ooh. Knock, knock. I know two things. How many amps do I lose in this topmost resistor? How'd you get that? Okay, so we're using V equals I times R, and I equals V over R, and R equals V over I. And eventually to find power, we'll use power equals V times I. So I agree with you. 3 amps. How many amps were coming into this junction?
5.
How many amps must be going through that bottom one then? And I could also get that by going 30 divided by 15. No matter what, I'm getting 2 amps. Okay? Ooh, Owen, how many amps are going through this 4 ohm mathematically equivalent to the right-hand side? Yes. How many volts do we lose going through this right-hand side then? Xavier, how many volts am I losing in each of these branches then? Ooh, I can tell you the current is going to be 20 divided by 20. And I hope, is the other one 4 amps? It would sure be nice because they have to add to, is 20 divided by, or, yes! 20 divided by 5 is 4 amps. Owen, how many amps do I lose going through this bottom section here? I use up going through, sorry, I've got 5 amps going through there. How many volts, Xavier, do I lose going through this bottom section then?
30.
Which means you're telling me each of these is 30 volts and 30 volts? How many amps? Now remember I said something like, I think it might, identical resistors might split it up exactly into 2.5 and 2.5. Is that the case when you go 30 divided by 12? Oh, nice. But this is also why I said you can survive just fine without that. Could you find the power loss in each resistor by going V times R? Sorry, V times R. V times I? Is that correct? You could. It's getting too cluttered. So scribble out power lost in the instructions because it's just getting too cluttered. Okay. By the way, if this was a test question, it'd be worth 7 marks, and it would probably be something like this. Find the power loss through the 12 ohm resistor at the bottom. And I would know that to do it, you had to find everything else first. I'll contrive it that way so that, I got to find about 5 other things before I can get there. Ideally 6 or 7 other things so I can give you your 7 marks. That's for the test writing. But this is why I really like solving circuits. I find the little Sudoku puzzles where you find one thing and you can find something else and go from there. Okay? So example 8 illustrates a very important point. It shows us the voltage drop across parallel resistors in the original diagram is the same as the voltage drop across their mathematical equivalent. 30 volts, 30 volts, 30 volts. 20 volts, 20 volts, 20 volts. Okay? That's a really handy trick to have in your back pocket, Sarah, to jump from your rough sketch to the original. In a household circuit, this is going to be AC. The symbol for AC is this, a round thing with a little sine wave. So can you put a little sine wave in there? That looks terribly messy. I couldn't get it to go in Word when I was typing, but it should look like an S on its side. Okay? In a household circuit, plugs and lights are wired in parallel to 120 volts AC. Each circuit has a circuit breaker in the circuit, and when the current goes above usually 15 amps, then your circuit breaker will trip for safety because that's going to generate too much heat in the wires, and fire is bad. So, if we connect a 1200 watt hairdryer and a 500 watt TV to the same circuit, will we cause the breaker to trip? Let's do a quick circuit sketch. So we have a voltage source. It's AC this time. But let's pretend the current is going up, just because what I'm teaching you for direct current does work for AC. And then here we have a resistor. And here we have a resistor. And they've told me that this is 120 volts. I'll put the AC there. And the hairdryer has a power of 1200 watts. And the TV has a power of 500 watts. Let's see if we can solve this. Now, I'm going to say which way is the current flowing. In AC, it flows in both directions, but let's just pretend that that's downhill, because that's what we usually labeled first. In real life, it just goes back and forth, back and forth, back and forth, back and forth. Do I know how many amps are leaving this particular circuit? Nope. Do I have amps anywhere? Really? You see an A somewhere? Do I have amps right now anywhere? Okay, check that off. Do I have two things anywhere? Right now, you see a resistor that has two things on it right now, this moment in time? Say no. Okay, that's my procedure. Can I get total current? No. Hey, can I find amps anywhere? Because often I can find total current from that. No. Okay, two things, because if I can find total current from that, no. Now I'm going to ski. Darman, how many volts am I gaining right here? How many volts do I lose going down this branch? And 120 volts. Now I can tell you how many amps must be going through here, because I can use power equals V times I. I guess I is power divided by voltage. How many amps are going through this hairdryer? How many amps are going through this TV? What's the total current going through this circuit? How many amps before I blow the breaker? The question told me. Am I going to blow a breaker? I'm close. Plug anything else in? Yes. So this is my message to all of you, both in your current houses and as you move out. Like, if you plug an item in and the breaker blows, don't reset the breaker and then stupidly plug the same item in. The math is not going to change. You need to unplug something. There's too many objects pulling current from this specific circuit. Zach is going, wow, I always just tried resetting it, plugging it in again. I know you would, which is why I'm telling you don't do that. Because repeat after me, fire, bad. Fire bad. In a related note, none of you ever want to room with Zach. What's your homework? 1, 2, 3, 4, 5 is good. Oh, did I assign 5? Sorry. 6 is good. That was mean of me. Didn't even notice. I wish I'd been doing that to be funny. I'll skip 7. 8 is good. Skip 9. 10 is good. 11 and 14. 15, here's an old provincial exam question. Okay.